So as I was saying that there are two different perspectives for variational autoencoders. One is the neural network perspective. You just view it as a neural network and just list down the operations. Do the standard thing. What do we do with neural networks? We write down what the model equations are. How do you get the output as a function of the input? What's your objective function? And what's your learning algorithm? If you do that, it's just the neural network perspective. The other perspective, of course, is the graphical model perspective. You think of these things in terms of random variables, dependencies between random variables, and then certain things on top of that, right? So we are going to look at both these perspectives. So we'll start with the neural network perspective first, and then go on to the graphical model perspective. Okay, so once again, our setup is that we are given some images. So they are given some n images, and we can think of images as a collection of random variables. Each image has 1024 pixels. So your x is of dimension n in general, or in the case of images that we have been taking 1024, right? So that's your training data. And for each x, or for each of these images, the dimensions correspond to the pixels in the image. Now what we are interested in is learning an abstraction that had given us x, we are interested in learning a hidden representation z. So here what I've shown you is actually a two-dimensional hidden representation. So assume you just have z1 and z2 as two dimensions. And what I've done is, for all the inputs that I had in my training data, right, for all the images that I had in my training data, I just computed this two-dimensional representation for them and just plotted them. And these are probably all the images of beaches. These are all the images of mountains, say. These are images of buildings and so on, right? So you can see that things which are similar, they'll have a very similar or clustered hidden representation, and they would all lie very close to each other, right? So that's what an abstraction means, right? You just take this high dimensional image and then try to learn a low dimensional representation for that. And in that representation space, things which are similar but were not so obvious in the high dimensional space come together in the low dimensional space, right? That's the whole point of abstraction. And the other thing that we are interested in doing is generation, that if I give you a hidden representation, you should be able to generate data back from it, right? So suppose I'd learn hidden representations for faces. Now if I give you a hidden representation, you should be able to give me faces back, okay? So these are the two things that we are interested in. And in probabilistic terms, what we want is, we want a distribution over the latent variables given the observed variables, and a distribution over the observed variables given the latent variables, right? This is the drawback or the limitation that we had in autoencoder, and this is what we want to fix in variational autoencoders, okay? Right. So I mean, what's the big deal, right? I just told you that I'm going to give you a neural network perspective, but you have already seen a neural network which can do this, right? You have already seen RBMs, which does exactly the same thing. It's a neural network, it's a stochastic neural network. It gives you both the distributions P of z given x and P of x given z. So why, I mean, this module just ends here, right? I've given you a neural network which can adhere to your wish list. So why do you want to do something different? So the answer actually comes from literature on graphical models in general. So the idea is that all algorithms or models that you see in all graphical models or generative models that you see, they always have a lot of assumptions. These assumptions are either in the form of independencies, or they are in the form of approximations that you do while making certain computations, or they are expensive because you need to do something very expensive like a Markov chain and so on, right? So I'll just list down some characteristics. I'll not call them limitations, because almost all the models that we'll see, starting with variational autoencoders to autoregressive models and later on GANs, they all have their own set of limitations. So I'll not call them limitations, I'll just highlight some characteristics of RBMs, and then later on we'll try to compare them to variational autoencoders, which I'll probably do in the last lecture once I finish all the deep generative models that I want to cover. So here are the characteristics, right? First thing that we do is, this was a Markov network where we had made certain structural assumptions. What do I mean by that? What were the assumptions, structural assumptions that we had made? The hidden variables do not depend on each other. The visible variables do not depend on each other, and they only, so we had assumed this bipartite graph, like whatever is visible in the figure, right? So that's a structural assumption that we made. It's not clear why we made that assumption, or what should that be the necessary thing, or could that have been different, or whatever, right? So that's one assumption that we made. The other was in terms of computational, right? So when we are doing RBMs training using Gibbs sampling, remember we were doing stochastic gradient descent, and at every step of stochastic gradient descent, what did we have to do? We had to run this Markov chain. And we always got away by saying that just run the Markov chain for a large number of steps. In practice, that large number of steps can actually be very, very large. In theory, of course, it is as n tends to infinity, right? So all those guarantees hold only asymptotically. That means only if you run the Gibbs chain for an infinite number of time steps, right? But in practice also, you need to learn it for a large number of steps, right? And that leads to some computational limitations, okay? The third was approximation. And this is what we had done when we were doing contrastive divergence, where we had done this nasty approximation that this entire summation, which should have actually contained 2 raised to n terms, we just approximated it by a point estimate of one single term. Do you remember that? Right? In contrastive divergence, we just took one negative sample and approximated the second summation by that sample, right? So these are some of the things that we did in RBMs. You might do a similar set or a different set of assumptions and approximations in the case of VAs, right? The point is, there's nothing wrong with any of these. I'm not saying that this is why RBMs are bad. It's just that we need to be aware of these, and such or similar limitations or characteristics we'll see for all the different deep generative models that we're going to talk about, right? So variational autoencoders might have something different. So hence it's good to have these multiple flavors of these models. Each one comes with their own set of properties, and whatever suits you best for your application, you could rely on that, right? That's why we're doing multiple of these. So starting with RBMs and now looking at variational autoencoders, okay? So that's why the neural perspective does not end here. This is just one possible neural network based solution for learning this joint distribution, but there are others possible, and we're going to look at those also. So with that background, let's return to our goals. So our first goal was to learn this distribution Q of Z given X. The second goal was to learn the distribution X given Z. In VAs, you use a neural network based encoder for goal 1 and a neural network based decoder for goal 2. Now, based on this initial recipe that I gave you, do these two statements make sense? What do I mean by these two statements? That I use a neural network based encoder to learn Q of Z given X and a neural network based decoder to learn P of X given Z. What does that mean? What am I going to do? No, just go back to the recipe that I gave you at the beginning of the lecture. I'm going to represent P of X given Z. What are the parameters of this distribution? I don't know, because I have not told you which family it belongs to, right? I could assume it's a Gaussian, I could assume it's a Bernoulli, I could assume multinomial, whatever I want. But what this high level recipe tells me is that I could choose any family. That family would come with its own set of parameters. In fact, let me give you the family. The family is going to be Gaussian, because for VAs, everything that we look at, we'll make Gaussian assumptions that all these distributions that we care about follow a Gaussian distribution. Now, if I'm going to make that assumption, what are the parameters of a Gaussian distribution? Mu and sigma. Now, what do I mean that I'm going to learn this using a neural network? I'm going to express mu and sigma as a neural network function, which is this complex function, and it has some parameters theta, and so my objective function is going to be with respect to theta, right? Do you get that? So can you relate this to the original recipe that we had seen? Of course, the details are still missing, but I want you to keep the high level picture in mind. How many of you get this? Please raise your hands. Okay, good. So now we look at the encoder first, and as I said, right, so it will take me almost the entire 35 slides to get to the full story. I'll deliberately skip some, you'll not probably realize it, but I'll deliberately not give you everything when I'm talking about the neural network perspective. Things will become clear only when I talk about the graphical model perspective, right? So if you feel there are some things missing, just wait till the end of the lecture and see if everything becomes clear, right? But as of now, I've not told you much, so there shouldn't be anything missing, right? So let's go ahead with that. So again, the same question, what do we mean when we say we want to learn a distribution? We mean that we want to learn the parameters of the distribution, right? But what are the parameters of QZ given X? I said I want to learn this distribution, that's very clear. And when I told you that, you also told me rightly that what I'm actually saying is I want to learn the parameters of this distribution. But what are the parameters of this distribution? No, that's the parameters of the parameters, right? The weights of the neural network are the parameters of the distribution. But what are the parameters of the distribution? So I have not told you that, right? So now I'm going to introduce that. It depends on our modeling assumption, right? What kind of family do we assume for P of Z given X? In variational autoencoders, we are not going to deal with arbitrary families, right? So we are going to assume a certain family for the distribution and then try to learn the parameters of that distribution, okay? Do you get the difference? Right? One is I tell you this is a joint distribution. I don't care what kind of family it belongs to. It could just be any arbitrary distribution, right? So it could be a distribution of the following form, right? So if this is my X, one dimensional, then it could be a distribution of this form, right? But what we are going to assume is that the latent variables actually come from a normal distribution, right? And we are also going to assume that the normal distribution is 0, I, okay? So now what's the job of the encoder? It has to take as input an X, and what should it output? What should it output? The parameters of this normal distribution, right, which is mu and sigma, okay? I'll just leave it at that and I'll come back to it again, okay? So now the encoder part is clear because I've assumed that the distribution Q is actually going to be a normal distribution which has parameters mu and sigma. So this mu and sigma, I'm going to express it as f of theta of x, right, where f is, what is f? A neural network, right, and theta are the parameters of the neural network. It takes as input x and gives me the distribution over z, or rather it gives me the parameters, right. Now the advantage of working with a family of distributions is that the only thing I need to give you is the parameters of the distribution. Once I give that, you can sample things from that distribution, right. So once I tell you that this is what my normal distribution looks like, and this almost looks like a standard, but if it was not a standard distribution, if it was something like this, once I tell you what mu and sigma is, now you can generate samples from this, right. So you can generate z's from this distribution if I tell you that this is what z given x looks like. Do you get that? Okay. So that's the advantage of working with a family rather than working with arbitrary distributions, okay. Fine. Now what about the decoder? So what is the decoder going to do? So this is what the encoder has done, right. It has taken an x, it has mapped this through a sufficiently complex function of parameters theta, and it has now tried to produce mu and sigma, okay. What is mu and sigma? They are the parameters of the distribution. Now what is the input to the decoder? Is it mu and sigma? What does the decoder do? It takes a hidden representation and tries to reconstruct the input, okay. But now there is some misunderstanding between the encoder and the decoder, right. In an autoencoder, they had perfect understanding. The encoder produces a hidden representation, the decoder takes the hidden representation and tries to reconstruct something. But now the encoder has fallen apart, right. What it is saying is I will not produce a hidden representation, I am just going to produce mu and sigma. But what will the decoder do with mu and sigma? It cannot work with mu and sigma, it needs to work with a z. So what will the decoder do now? So what do you have to do? Sample from this distribution. So the encoder has told you what the mu and sigma is. Once you know what the mu and sigma is, you can sample from that distribution. Everyone gets that? Please raise your hands if you get that. Okay. Now, when I say sample, the obvious statement which I'm going to make is it's not deterministic anymore, right? So if I'm going to say it as many times it takes me to say it, but this is your z-axis, and this is the distribution which I have assumed. In the case of normal autoencoders, you could produce only one of these values, right? You just had a fixed z. Now I have given you this mu and sigma, and I could sample any of these z's. Of course, the probability of sampling would be proportional to the probability distribution, right? So the values which are closer to the mean are going to be more likely, okay? But it's still going to be, there's still going to be some randomness in that, okay? So I'm going to sample from this distribution, okay. Now once I've sampled from it, the job of the decoder is to predict a distribution over x's. So now I've given you z as the input, and now I'm interested in learning a probability distribution over x's. Okay, that's what the decoder is supposed to do. Once again, we'll assume a certain form for this distribution because by now it should be obvious that you can't really work with arbitrary distributions, or rather the other thing is obvious that if you work with a family of distributions, life becomes much more easier, right? So we are going to work with images, say for example, and you could think of images as 28 cross 28 inputs. So they belong to this R raised to 784 space. So what would be a suitable family for such a distribution over real numbers? Again, I could assume Gaussian. There could be many other families, but I'm going to stick to Gaussian again, right? So again, I'm going to assume that it's a Gaussian distribution, and further I'm going to assume unit variance. What does that mean? Can you relate it to the assumption that we had made for RBMs? How many of you get that? Please raise your hands if you get that. What does it mean that the covariance matrix is identity or unit variance? All the off-diagonal elements are 0. That means all the random variables ij, where I is not equal to j, are independent of each other. Given what is the distribution that we are talking about? X given z. So this is the same as saying that given the latent variables, we are assuming that the visible variables are independent of each other. So this is very similar to the assumption that we had made in RBMs, but a different way of arriving at the same assumption, right? Do you get that? Please make that connection. Everyone is fine with that? Okay. So now we assumed it's a Gaussian, and further we have made life even more simple that we have assumed it's a unit variance. So what do we need to predict now? Only the mean of the distribution, right? So we just need to produce the mean of the distribution, and what are we going to do again, following our recipe? What's the input to the decoder? Z. We are going to predict mu as a function of, come on, Z parameterized by some parameters, and we'll call it phi, okay? So the encoder parameters are theta and the decoder parameters are phi, and although it looks different, we have actually followed the same recipe for the encoder and the decoder, right? We assumed a form for the first distribution, expressed the parameters of that distribution using a neural network with parameters theta. We assumed a form for the second distribution, expressed the parameters of that distribution using a neural network with parameters phi, and now our final objective function, whatever it is, I have not defined it yet, is going to be with respect to mu and sigma. Everyone? 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 Theta and phi, right? It's going to be with respect to theta and phi. Is that clear? Anyone who is not clear with this, please raise your hands if this is clear. Okay, I see a very small set of students. So people who did not raise hands, please ask me specific questions. 4,2. Yeah, you. No, the one before you. You're done. So you don't want to raise your hand. Even the lazy ones, please raise your hands again if you have understood this. Everyone, please raise your hands. Okay, now it's fine. You guys are just lazy. I mean, how much does it take to raise your hands? Okay, so I assume this is clear. We have followed the same recipe. It's the same as what I started the lecture with, right? Okay. Now, I've very conveniently told you that the optimization is with respect to theta and phi, but I've not even given you the objective function, right? So we need to first figure out the objective function and then ask those nasty questions that we had in RBMs, whether the objective function is tractable or not. Because we came up with a nice objective function in the case of RBMs, but what was the problem there? Computing that required an exponential computation, right? Because we had this expectation over 2 raised to n plus m terms, right? The summation was over 2 raised to n plus m terms, okay? So what would be the objective function of the decoder? What should we maximize? What is the decoder trying to learn? What's the decoder trying to learn? A probability distribution, P of x given z. What did I give you as the super input? X. So what should the decoder better do? Maximize the, remember the recipe, maximize the log likelihood of the input that I gave you, right? So what's the objective function? Maximize log of P of x, right? For all the n training examples. Everyone agrees with that? Okay. Now it should, now for this one given example, it should just maximize P of xi, and now just a shorthand notation, right? So when I say P of xi, it means P of x taking on the value xi, right? Okay. Now this of course can be written as the following integral, which is very easy to compute. How many integrals are there actually? So it's actually, when I say integral with respect to z, z itself is a vector, right? So this is integral with z1, z2, z3 up to zm, right? The number of dimensions that z has, right? So this is again a very nasty integral, and this is actually again the same kind of expectation that we were dealing with in the case of RBMs, right? Not the same expectation, but the same kind of expectation, where you have this term inside, and this integral is nothing but the expectation of that term with respect to, okay. So that's the problem that we have. We again are left with this. Was he in the wrong class? Or? Okay. And as usual, we take the log for numerical stability, right? So we have again come back to the same kind of story that we want to maximize the log likelihood, but it's very hard to compute and so on, right? But I'm just going to keep it at that for now, and we'll come back to this question. I just gave you the intuition that is going to be hard, but I'm just going to write it as it is, that this was my objective function, or rather this was my objective function with respect to one training sample. And if I want to consider all the training samples in my data, it's just going to be the sum over all the training samples, right? Okay. And is that all? What is the other thing that we had? Remember, we wanted to learn two distributions. Does this objective function capture both the distributions? It only captures P of x given z, right? What about the other guy? Do you get the question? Right? All I'm asking you to do is maximize this quantity, but this is just the circle quantity, which is just P of xi given z. That was one of the two distributions that I was worried about. The other distribution was Q of z given x. Is there anything in the objective function which takes care of Q? What is the constraint that I wanted on Q? What did I want Q to be? What did I start off with? I assume that Z is Gaussian with zero mean and unit variance. Based on that, can you give me a constraint so that I can add it to the objective function? The first term is clear, it's just the log likelihood of the data written in that fancy expectation form. Okay, but it's just P of x, that's all it is. Okay. The second term has to do something with Q. I want Q to be as close to a normal distribution, standard normal distribution. How can I convert this English sentence into a equation? I want to, but we don't like to do square errors when we are dealing with probability distributions. I have a distribution Q. I want it to be as close to a normal distribution. So I'm talking about the distance between two distributions. So what should I try to minimize? The KL divergence between the two distributions, right? So now what I'm going to do is to take care of the other guy that I care about, which is Q. I'm going to add this constraint that, and I've just, so I was talking about maximizing. So that's the same as minimizing the negative of the log likelihood, right? And minimizing the KL divergence between the two distributions, right? Where I have assumed that the second guy, P of z, is a normal distribution. Does this story make sense? Okay. So we have seen the entire neural network. We have seen what the encoder is going to compute. We have seen what the decoder is going to compute. Now we have come up with an objective function which has two terms. The first term takes care of the objective of the decoder, which is to maximize the log likelihood of the data. It better constructs samples which look like your data. And the second term tries to take care of the other intention which we had is learn a distribution over the z, but try to make it as close to the normal distribution. Is that fine? Okay. Now, of course, the question comes whether this loss function is differentiable, is it tractable, can I easily optimize it? Those questions I'm not touching at this point. We'll come back to them later. Okay. So the second term actually, let's focus on the second term again. So let's assume this is our objective function and we are not worried about computational aspects as of now. Whether I can compute these terms or not, I'm not worried about. Even I know that there's a nasty integral sitting over here. Okay. Now the second term actually acts as a regularizer. So remember now this loss function looks eerily similar to, remember this from way back 5 years back or 10 years back or maybe at 2 months back. Remember this form, that this is the loss function over the training data and you add some regularizer on top of that. So now can you think of these two terms as the first term which corresponds to the likelihood of the training data, and the second term actually corresponds to some kind of a regularizer, right? So what it does is that ensures that the encoder does not cheat by mapping every x that I feed to it to some unique z. Okay, so I have some x's. We actually come from some distribution, right? It may be normal, it may be something else, but it's some distribution, right? The x's, because these are all images of beaches, these are all images of mountains, so it might be a multimodal distribution, one mode corresponding to beaches, another mode corresponding to mountains, and so on, but there's still some distribution. Now if I don't add any constraint, what it could do is, what the encoder could do is, in the z space, it could just map each of these guys to a unique guy, right? And then the decoder, now it's easier for the decoder, it's just a lookup that whenever I see this person, I just need to reconstruct this guy, right? So it could do this kind of a cheating where it does not really try to capture any latent representations in the data. It does not really try to make sure all the mountains are close together or all the oceans are close together, but it just tries to do some mapping and then recovers from there. But now if I put a constraint on that these z's also need to come from a normal distribution, then it acts as a regularizer. It does not allow it to learn these unique mappings. So these mappings you could think of as zero variance mappings, right? Each of the z's has a very unique identity given the x. So that's the same as saying that there is no variance in the z. You give me an x, I'll just give you a fixed z. Okay? So this regularizer, this second term acts as a regularizer, and it ensures that you don't learn these unique mappings. And the other thing that it ensures is that I'm learning a distribution over z, okay? And now if in the case of an autoencoder, I was given a single z, and the job of the decoder was to reconstruct from there. But now since I'm sampling from this distribution, I could even sample a noisy z which comes from this distribution, and the decoder now has to be robust to this noise. Even if I give it a z which comes from this distribution, it's noisy, it should still be able to reconstruct the input. Okay? So that's how you should view these two terms that are there in the objective function. But now this critical question, right, which is there on the last bullet. Okay, I'll do it. So why do we choose a normal distribution? So what we are assuming is that these latent variables actually follow a normal distribution. Why a normal distribution? And what's the first thing that comes to your mind? Like, it's of all the possible distributions, I have first restricted the family. I have said only Gaussian distributions. Within Gaussian distributions, of all the means and variances possible, I have just said that this is a standard normal distribution. So doesn't that look too restrictive? Isn't it a very strong assumption that z belongs to a normal distribution? And since the figure is already there, the top figure is actually trying to show you data which comes from a normal distribution. So you can think of it as a bell from the top view. So you're looking at the area under the bell, right? So this is all the things are, there's high density under the bell, right? So the circle under the bell. So why did we assume something like that? What if the z's were actually distributed like what I've shown in the second figure? No, but we are not using that, right? What we're doing is we're just assuming that z's are come from a normal distribution. But what if z comes from such a distribution, the second figure? And that's where you need to connect everything back to a neural network, which is the theorem that he's referring to. So can you relate it to that? Okay, so we'll try to complete that story, right? So in the two-dimensional case, right, why should it be a normal distribution like the figure 1? It could be any arbitrary distribution like the figure 2. But the key insight here comes from the following observation that, and this has nothing to do with neural networks, this is just normal probability and statistics, that you can start with a set of d variables which are distributed normally, right? In our toy example, d is equal to 2. So I could start with a variable which is distributed, two variables which are distributed normally, and from this I could map these variables through a sufficiently complex function and create any arbitrary distribution. What does that mean? So I've drawn z from a normal distribution. So that means I'm going to get z's which come from here. Now what I know is that I could take such a z And you have to just take my word on this and maybe go back and read some of your probability and statistics notes. But just for now, just take my word for that. And I'll actually explain it in the case of this toy example. You could take a z drawn from here, right, and pass it through a reasonably complex function so that you start getting values which look like as if they had come from this other arbitrary distribution that you care about. Okay, so let me give you an example. In this particular case, right, for example, this complex function that I'm talking about is this function. So try this. You draw samples from a normal distribution, map it to this function, and then plot the values. You'll get back the circle that you see in the second distribution. So what I'm asking you is, go back and draw, say, around 1,000, 10,000 samples from a normal distribution, compute the following function for that variable, that sample which you have drawn, and plot it. And you will see that you will get this second thing. So what I have done is, I have taken a z, I have passed it through a sufficiently complex function, and then I know that I can go to any arbitrary distribution that I want. Now, what is a sufficiently complex function that you know of? Neural network. Hence, the decoder is a. So what does that mean? Can you tie these things together? I could make this assumption that it's a normally distributed latent variable. If it is not the case, then the initial layers of the decoder could learn this complex mapping so that I get to whatever distribution for z which is actually the real distribution for z, such that when I now compute x given z, it will maximize the probability that I care about. How many of you get this statement? Please raise your hands. Okay, good. So that's exactly what we do, right? So if you can pass these z's drawn from a normal distribution through a sufficiently complex function, and that function could have its own parameters which are phi, and the function that I'm hinting at is a neural network. And we know based on the universal approximation theorem that a neural network, under certain conditions of course, can learn these arbitrary functions of the input. Your input is z, which is normally distributed. The actual distribution that you care about is some complex function of this normal distribution. But your neural network, the initial layers could learn this, and then finally when you get the p of x given z, it would have come from a z which was the actual latent distribution and not the initial normal distribution that you had started with, right? Does that make sense? Okay. So what it means is that if the decoder really needs to learn its parameters phi such that it transforms the z from the normal distribution to an arbitrary distribution, and only then its objective function would be maximized, then the decoder will do that. Okay, the decoder can do that because its job is to maximize the objective function, and to maximize the log likelihood, if you need to learn this transformation for z, the initial layers of the decoder can do that. Okay, that's why it's fine even if we start with a normal distribution. Is everyone clear about this? Please raise your hands if you are. Okay, good. So that's where we'll end the neural network perspective of variational autoencoders. And I'm ending on this sad note that I haven't actually told you whether this loss function is tractable. If it is tractable, how are we going to deal with it? I have not really told you about that. Okay, so we'll come back to that later on. But for now, this loss function makes perfect sense from the neural network perspective. It's very similar to everything that we have done before, that you want to maximize the log likelihood, and that's just, this loss function just follows from that. And the additional constraint was that you want the latent variable distribution to be close to the normal distribution. Okay. So that's where we end the neural network perspective, and now we'll go to the graphical model perspective.